So let's get started. Welcome one and all to the inaugural session, the 2022 session of UDYAM'. So this is actually the inaugural speaker session. So I'll just play the teaser right now, and yeah. So today's session will be conducted by NULLCON. So Mr. Yashodhan Vivek Mandke and Mr. Appar Thusoo will conduct the session. It will be about introduction to IoT hardware hacking. So I'd like to hand it over to them so you can get on it. Thank you.
Sure, thank you so much. I'll share my screen now. Please let me know when it is
Yeah,
visible.
yeah, you can share it. Yeah, it's visible now. Yeah.
Yeah, all right. Thank you everyone for joining in. Uh, my name is Apar, and with me today is my colleague Yashodhan, and we'll be basically, giving a 101, a primer on introduction to IoT hacking. So for today, we have kept our agenda very crisp and clear. It is going to be introduction to what IoT is, which I'm sure a lot of you already know. What are the IoT attack surfaces that a hacker or an attacker can basically target in order to get the access of the device? Then what goes behind the scenes? What is IoT security assessment or hacking methodology? Uh, then we'll dive deep into what is IoT security compliances and standards. One should stick to in order to create a secured product by design. And finally, we'll go into specifics of hacking and we'll look into the hacking of IoT device hardware or the embedded hardware. And finally, how you can hack the embedded device firmware or what are the underlying issues with it. So let's get started. So this is from the internet. So what is IoT? I'm sure every one of you know what is IoT. So it is a concept where all the things basically get connected to the internet. It can be smart dash X. It can be a smart toothbrush, a smart chair, a smart pen. Anything that connects to the internet is an IoT device. This term was first coined by Kevin Ashton in 1999. Some facts for the soul. And apart from that, basically the concept, the purpose behind introducing IoT was majorly to have remote access to objects, some interfacing some sensor. You can get some data out of the environment and process the data and produce or have a stimulus or some action based on the input data. So yeah, IoT has been growing exponentially since then, and by 2025, the number is expected to rise to 75 billion devices. So again, what the purpose was, as I mentioned, it was automating some of the processes and uh, processing the real-time data. The actions that it can produce, it is majorly, if we talk about a high level action of the IoT device, it is basically sensing and actuating, sensing the environment conditions, and then based on that actuating an action by the device. IoT has been, given different names. It is called IoT. It is also called IIoT when it comes to industries like the industrial IoT or the automation industry. I'm talking about the heavy or manufacturing industry. So there it is called IIoT. When we talk about critical infrastructure like your power grids, your water treatment plants, their IoT can be called cyber physical systems. Um, when the IoT is implemented on uh, uh, you know manufacturing line, the robots and the manufacturing line is connected to the internet. It is called Industry 4.0 and also connected devices. So IoT, I'm sure all of you are aware that it is now in almost each and every domain, starting from industrial or manufacturing to home automation to your consumer or lifestyle electronics. I'm sure all of you must have a smart band or um, you know e-scooter, uh, whatnot. Enterprise, a lot of enterprise devices are getting connected to the internet. For example, your CCTV cameras, your printers, gateways, and the list goes on. Medical devices, there's a huge surge, especially in the last couple of years that we have observed that medical devices are also getting connected to the internet. So medical devices, again, there's a wide category. Some of the off-the-shelf medical devices, like your BP monitoring machine, your glucose monitoring machine, while some of uh, the class zero medical devices, which include your pacemakers or your defibrillators or any of the insulin pumps or the other things that go inside the body. So everything is getting connected to the internet, which is of course uh, scary, but at the same time it is also cool to see how the technology is evolving. Smart cities, transportation, space tech. I'm sure you must be aware of all of this. Uh, so, what are the issues that when we talk about IoT? What are the issues that are seen on a very high level? So, IoT is relatively a newer market. A lot of startups, a lot of uh, you know teams or companies working on prototypes. Since there is not much defined when it comes to IoT, so it is a very new market, a very wild place to be in. Uh, Protocols and standards. There is a lot of protocols and standards that are put forth when we talk about software development or when we talk about the security of yeah, be it your web, your mobile application, uh, uh, and and so on and so forth. But when it comes to IoT, there is not much that we have seen when it comes to standards. All the new standards are coming into the picture, but it would still take up some time to for these standards to evolve into a more mature and dynamic standard, which we can confidently say that yes, adhering to these standards would ensure the security of your device. Again, too many vendors, a lot of vendors coming into the market, a lot of OEM manufacturers from, your Taiwan, Shenzhen area, China, and, some startups buying these uh, off-the-shelf ready-made devices and, putting them into the market, white labeling it. So, there's a lot of vendors that have crowded the IoT industry. Uh, and again, similar state to how software security was back in the 90s when hacking used to go back and forth, front, right, and center. Same as the state of IoT security right now. But there is very less to blame because IoT also comes with some restrictions, which is your power and cost, which is the main you know main barrier when it comes to companies working on the development of these devices. But that cannot be taken as an excuse that the device is insecure. But again, uh, a limitation when we talk about IoT. At a very high level, this is what the IoT device, what we can classify as a layered model of IoT. You have the management layer at the very top, which includes your cloud and the applications. Then in between, you have your communication layer, which basically consists of your networks. It can be wired network or some IoT protocol like MQTT, MQP, that is communicating with the cloud, or it can be your wireless networks as well, which can include your LTE network, Zigbee, BLE, whatnot. When we talk about different, scales of communication, and finally you have the device itself. At the device layer, you have the sensors that are taking these environment variables and collecting data from the environment, and you know basically processing them into a more uh, understandable uh, understandable form for the machines to send it further. So this is an example of the layered model. Now let's talk about the IoT attack surfaces. So as we know, IoT is not just one thing that consists of IoT. It is a compilation of lot of elements that are put together, which gives birth to an IoT device. Broadly classifying, we can say you have your network, you have your device, the cloud, and finally the client application or the mobile application, whatever comes along with that device. So talking about the device itself, you have a lot of different attack vectors that you can probably explore on the device itself. This comprises of your storage. By storage, I mean your flash memory on the device PCB. The communication. Again, by communication, I mean the onboard communication. Using your device using uh, protocols like I2C or SPI for inter-chip communication. Then you have your authentication and authorization. So let's say you find a UART debug on the device. It can be interesting to see whether it has an authentication on top of that or not, or it is just um, an open hardware debug header. Then hard coding. Hard coding comprises of hard coding your keys, your certificates onto the device, which is again a very common practice that we find on a lot of devices that we come across. Encryption. By encryption, we mean is the firmware encrypted? Is the data at rest, which means the data or the firmware which is stored in the flash, is it encrypted? Are there any encryption techniques or elements being used? For example, your TPM or your crypto element or your DRNGs, your random number generators, and so on and so forth. Um, Again, hardware debug ports. What debug ports are available on the device PCB? Now, it can be your UART, your SWD, your JTAG debug header. So, an attacker can basically use these hardware debug headers as an entry point to the device. So, making sure that these are hardened while your device is going to the production. Again, bus communication, as I mentioned, you have your um, electronic components talking to each other via the serial bus, um, and making sure whether that bus is uh, you know protected or not, whether it is encrypted or not, whether there are uh, you know uh, integrity checks or not on that communication bus. Then next is firmware storage and update, how the device is managing the firmware on the device. Where is it stored? Typically in a lot of devices that use Android, we find that the firmware is stored in eMMC, while in your low-cost device, we find that the firmware is stored in some sort of SPI flash or your NAND flash. Also the updates, how securely the updates are taking place. So this is just, we talked about how the device as an attack surface, can be exploited by an attacker. And in most of the cases that we see, a lot of 0 days or, you know, 0 days are the kind of vulnerability that even the device manufacturer doesn't know about or hasn't, charted out the vulnerability in their threat modeling. So such 0 day vulnerabilities we have observed that comes when an attacker is basically exploiting the device itself. So the device provides an entry point, then the attacker would use this extracted firmware, understand the logic, use some reverse engineer some custom binary provided by the manufacturer, and then you know uh, write an exploit to exploit a huge class of devices. So this is how the device itself, the device hardware is a critical component in the entire IoT attack surface picture. When talking about network, you have different custom IoT protocols, your MQTT, COPE, AMQP, XMPP, UPnP. So there's a wide set and a huge list of IoT protocols that everyone is implementing. All the vendors are implementing. Some of the vendors have their own custom protocols as well, which is uh, which is kind of funny because we have observed that a lot of these custom protocol tend to be insecure by design. And lately news came up where uh, there was a huge one of the leaders in medical devices called Medtronic. They were using a custom protocol on one of their um, pacemakers, and it was found to be vulnerable. So uh, companies are trying to implement things their own way, but security is something that is usually lying on the back seat. Similarly, radio protocols in communication, you have different radio protocols that are specifically seen in IoT products. Now, this includes Zigbee, your BLE, your LoRaWAN, and your wireless HART. So again, these are standard protocols that are implemented, but again, the implementation varies from product to product, and that is what the attacker also looks forward to while exploiting the device. Then encryption on these network and related protocol vulnerabilities. And for example, if some network is using TLS 1.1, something like that. So uh, so the TLS 1.1 is you know TLS 1.1 is contains a lot of known vulnerabilities which an attacker can exploit in order to gain access to the device. So this is how network plays a role in the attack surface, and this is how attackers usually tend to target the wired or the wireless network in these devices. Then we have the mobile and client application. This is a very well-defined field now. I think a lot of organization like OWASP have, you know, come forth and um, defined a lot of, guidelines when it comes to securing these assets, be it web, mobile, thin client application, and so on. So again, the attackers usually look for the storage, like talking about mobile application, whether the storage is the application is storing the data in a proper manner or not, whether there is authentication or not, whether there is hard coding of keys or not, encryption is being taken care, and then generic mobile vulnerabilities that you can also read about if you just look up OWASP top 10 for mobile. So again, mobile is also an attack surface because it is the remote element or the client-facing element, and is of more interest to the device, more interest to the attackers because their objective from the client side is to basically gain some kind of access to the cloud, and then finally from the cloud, have the access to the devices. And last but not the least, we have the cloud itself. So cloud is also now one of the more defined and standard uh, field when it comes to the security terms, because we have a lot of security guidelines being published in terms of cloud. Again, storage and communication, how these devices are um, storing the data on the cloud and how these are communicating. Some of the examples are AWS IoT, Microsoft Azure ID. Again, these are not vulnerable by design, but again, the implementation or the misconfiguration is what leads to the compromise of the cloud as well. So again, that serves as an attack surface to the attacker. They check whether the cloud is properly uh, configured or not, and whether there is any sensitive instance that is exposed directly on the internet or not. And again, authentication, authorization. Uh, there's one funny incident that I'll share with you. So we were assessing this device and we were able to dump the firmware. And we unpacked the firmware, and the first thing that we came across was the AWS certificates and private key, which was funny because that is something that should be stored in a more secure way on the firmware. But nonetheless, cloud is also one of the major targets of the attackers. Then you have APIs and then your generic web and cloud vulnerability. So by now, I'm sure you must have gotten an understanding that the test coverage for an IoT device, is very vast. It starts from your protocols, third-party softwares, libraries that are being utilized in the uh, in the device. Then you have your user interfaces. User interfaces generally linked to whatever business logic is being implemented on the device. You have your cloud, your encryption, next is your authentication, authorization, and I think uh, auditing or logging, basically AAA. Then you have your firmware and hardware. So the test coverage is very wide, and while we perform security assessment as part of our research or projects on the devices, there is a lot of elements that have to be probed, and likewise is the case with the attackers as well. So, giving you an example on some of the test cases that can be performed on the device hardware. So on top, you can see the device hardware. Breaking it down, we have 6 different elements of the device hardware. We have the debug port testing. We have the bus communication testing. We have the transducer manipulation. We have the USB testing, data extraction, reverse engineering and analysis, and radio communication testing. So this is just an example of some device hardware that has all these different elements. And again, it varies from device to device. So while talking about debug port testing, you have your different debug protocols like JTAG, UART, SWD, and as an attacker or as a security professional, you will go around testing for whether these debug ports are properly hardened or not, or whether there is proper implementation like authentication on top of these debug ports or not. Then next you have your bus communication testing. You have your different serial communication protocols. Working in and out on the PCB. You have I2C, SPI, UART, even CAN, LIN. So these different bus communication protocols you have to basically sniff from the hardware and then analyze the sniff packets and try to find data of sorts or check if the implementation or the encryption is implemented properly or not. Next is transducer manipulation. You have your different sensors and actuators on the device, so you can check whether you are able to manipulate the sensor data. Again, it is your normal uh, digital data for some sensors, while it is your analog data for some sensors. Then USB testing, if there is any kind of micro USB or your USB A available on a device, we basically go about first testing first testing the USB uh, driver. So you connect some, you connect it to a system, and then you first test in order to see whether the driver that is responsible for handling the USB data is it able to also undergo some stress tests like first test, or it can even some stress tests can also lead to denial of service on the device. Then you have your data extraction and reverse engineering. Now, this basically comprises of data extraction from the memory chip, um, and your uh, microcontroller and firmware. Now, once the data is extracted, once the firmware is extracted, you go about reverse engineering the firmware. Uh, while we go ahead, we'll look more into what a firmware is, and how you can check for security on a firmware. Then finally, last but not least, is your radio communication testing. Basically, uh, if a device is using, let's say, if it is not using a custom protocol, it is using some raw RF, uh, in your ISM band, you can check for reverse engineering, how the bit stream is being on the link is being communicated from one place to one device to another, from your sender to your receiver, replaying that stream and checking if there is any kind of replay attack possible, and malicious command injection. You change those bit streams. You try to see if you're able to inject some kind of malicious command onto the receiver, and again that questions the integrity check of the receiving end. Then just a quick flow on how the IoT product security testing process goes on. So this is an insight of how we do it here at Payatu and Exploity. So you have the requirement gathering phase where we first try to understand what the requirements are from these different device product companies. Then we go about scoping on on how to scope the different attack surfaces, because a lot of companies that come for us for the security assessment of these devices, they say that we are not interested in assessing our cloud, or we are not interested in assessing our um, AOSP implementation, stuff like that. So, we sit down with them and try to understand what is exactly that they think is a threat to their business and to their product, and then we go about, working on that specifically. Then we have the knowledge transfer, where basically the development teams or the product teams sit along and tell us how the device works. Again, it depends on um, what kind of assessment it is. If it is a white box assessment, we as a company would sign an NDA with them. They would give us their architecture, maybe their source code, some of the data sheets of the microcontrollers they are using and stuff like that. And if it is a black box, which is on the extreme end, they would basically give us the device and just a walkthrough on how the device works, and rest is for us to figure out. Now that ends where the company and the assessors have interaction. Now comes the part where the attackers or the security researchers start their work. Now the first thing is reconnaissance. Reconnaissance on the device. You break open the device. You look for what controllers is it utilizing, what DPMs is it utilizing, what kind of flash memory is it utilizing. You Google up all the stuff, you find the data sheets, you get an idea of what are the supported protocols and stuff. So reconnaissance is, one of the major and important phases of while we're talking about security assessment of the device. You can also go about, based on the model ID or the product ID, you can look up, different dark web forums, or even the clear web for some of the uh, threat intel. So that would basically give you, if some developer from XYZ company has published his source code on Stack Exchange saying that, hey, I ran into this problem. Can anybody help me out with this piece of code right here? And as an attacker, uh, we can also utilize that piece of code, find some vulnerability which would serve as an entry point into the device. And this is one of the incidents that we also came across where a 20-year-old piece of source code being used was on found on some uh, you know uh, these coding forums held in order to gain access to one of the printing devices. Then we have attack surface and threat modeling. So once we assess like what are the areas of interest and which which surfaces would have more um, sensitive data or will have more impact, we create a threat model around it. We try to identify these assets, and you know based on that we carry forward our assessment. Then once the threat modeling is done, we basically break down the assessment into parts. You have one team working on the mobile app analysis, one team working on the cloud assessment, one team working on the hardware assessment, and one team working on maybe wireless or the firmware. So once we have identified what the threats to the device are, we try to focus individually on exploiting or turning those threats into vulnerabilities. And next is, once we have found some vulnerabilities, we try to report it. We compile all the POCs, we compile all the screenshots or the POC videos, and then with that we put a cherry on top with some recommendations on how these vulnerabilities can be fixed at a broad level. Uh, Once this is done, these reports are then out provided to the companies, and then they would fix these bugs and come back to us if retesting is also in scope. It is in order to check if they have properly patched uh, or hotfix the vulnerabilities. So this is a brief, not a brief, but a very uh, high-level walk around of how the IoT product security testing process works. So now I would basically hand over to my colleague, Mr. Yashodhan, and he'll be speaking about IoT security compliances and standards. So over to you.
Thanks, Appar. Hello, everyone. So I'm Yashodhan here. I'll be speaking around two factors. One thing, one unexplored area on the IoT security, which are the standards or the guidelines to design secure product or assess some of the IoT products from the security perspective, as well as I'll be speaking about the actual IoT hardware hacking part. So that will start in a moment. So as you can see over here, the reason being these guidelines or the standards, why do we need such kind of things? So of course, since a lockdown and those things, past 2 years, you might have heard about a lot of IoT device has been compromised, and there are $1 billion of business has been compromised in that scenario. Now, one challenge happens is IoT is basically a kind of a diversification. So just now, Apar spoke about many of the aspects. So even top of that, when you have a cloud and those things, and you have a lot of data from the sensors collected from the IoT devices, eventually, again, AI, ML, and those part also come into the picture. And all each of these layers, starting from your basic hardware, the firmware part, the communication part, web application, cloud application, and the ML part, everything can be attacked in a different way. And that's way to address all of these layers, the IoT actually needs kind of a standard or a kind of a guidelines to make the product secure. Of course, there are so basically what these guidelines or standard come with. So they come with certain kind of the verification and assessment checklist that one can follow and make sure your product is secure. So whether the IoT company, like whether you are IoT manufacturer or someone is developing some IoT products, so developing the hardware or developing the firmware for the microcontroller for that matter, or even if there are something called the system integrators who are basically collaborating with OEMs, which actually manufactures IoT devices, and eventually collect the data and integrate it through some different softwares. So all these things, different vendors come to the picture. If they follow certain security guidelines, it becomes easy for them to make their product secure. And that's why these compliance and security standards are there. So now coming to understanding of these things. So what kind of, the role of such kind of security compliance present to us? Now, there is something called as a level of security in which you're looking for. So think from the perspective that, let us say we have an IoT product which has the sensors like temperature sensor, pressure sensor, humidity sensor. Now, with a microcontroller, and let's say it has a Wi-Fi interface for that matter. Now, imagine this particular product when deployed into the meteorological department, the level of security required for that is kind of a minimal security, right? So even if someone is tampering with those, sensors and those things and trying to change the sensor values, the result of such attacks, right, is not that hazardous compared to the same product if it is deployed into, let's say, nuclear security plant, where you're trying to measure some of the critical kind of processes, trying, right, understanding the process when anything happens. So if someone tampers into that, it is more hazardous. And now, based on this use cases and the application, the IoT products security level keeps on changing. So when I spoke about these meteorological stations, where I want to put it as a data logger, the possibly the security level will come as security level 1 as a base level. And let us say if you go to the nuclear security plant, it goes to the level 4, which is the topmost level security. So this way, this compliance will help us to decide on what front your system is secure over there, or what class of security you can follow. Not only this, it also addresses some of the critical parameters like risk assessment. So when we say risk assessment, is that we create a kind of a threat model of a system based on, for example, let us say we create an architecture of a system where we have certain microcontroller, we have a sensors, we have other electronic devices. On top of that, we have an architecture of a firmware. Now, over a period of time, when you have this complete architecture ready, so there are technical architects sitting and doing all those things for a product. But eventually, there is a security architect who is responsible to look over all of these aspects of the security and eventually find out what are the threats at each and every layer over there, starting from the hardware, the communication, the firmware, the cloud, and every part. And he can address, okay, these are the challenges in the existing architecture, and we should create a better security architecture for the existing part. And for that matter, as a beginning, he starts looking for the threat modeling, considering for the fact that, okay, I have a hardware, what are the threats possible? So if I have an analog sensor, okay, someone can directly tamper into the sensor and can basically connect something into the analog pins of the microcontroller and start changing the data itself. So that is one of the threats to the system itself. Now, from that perspective, each and every part of your system is considered as an asset, and you address that particular security from the three foundations of the what you call cyber security. That is nothing but availability, integrity, and confidentiality. So when we say availability, for example, let us say you're trying to connect to some Wi-Fi, but eventually someone has compromised the Wi-Fi and you're not able to connect to that. Think from the perspective that if this scene happens into some of the critical operations or some mission critical operations, then this is a big issue for the security, because the availability of that Wi-Fi is issue. Then integrity is something where you have let's say data from different sensors you're storing over there, but someone is tampering into that particular data and trying to change those parameters. Eventually, that is the integrity issue with the data. And confidentiality is something where you are sharing something on a very private basis, and the data is being like it's accessible by someone else. So the confidentiality in that communication is being compromised. And these are the three basic pillars of any of the cybersecurity measures, and these compliance will address these issues. Now there are some security agencies, so IoT security regulatory agencies. As you can see, the names over there, like ISO is one, NIST one, National Institute of Standards and Technology. Then the OAPs, the Open Web Application Standards for that. Then there is something called as the IoT Security Foundation, IoT SF, GSMA, ITSI, right? So these are the different agencies who either develop some standards or a guidelines or a framework for the IoT security. So if we just go to the next slide, so you'll see all those abbreviations, what does they mean? Right? So each and every of these agencies provide some kind of guidelines and the standards. So when we say a guideline, it means that the guideline just helps you to tell, okay, you can do this to make sure your product is secure. And the standard is something like you have to follow this standard if you are coming into that particular framework, right? So let us say if you go to these standards, as you can see over here. So let's say compliance agency is ISO, and they have the ISO security standard like ISO IEC 27030 and ISO IEC 17825. These are more related to something like side channel attacks or something that on IoT devices. So these come under the standards, meaning that if you are trying to follow this particular framework, it means you have to follow each and everything from those standards, right? And if you just come down that other things over there, right? So NIST again comes with the IoT security standard called NIST 800-213. Right? It is again available for free. Then if you look at the OAPs, right, it is basically kind of a guideline. So they have very famous OAPs IoT top 10. What it says is like they have the basic 10 level of guidelines, which are quite abstract from the perspective of how you secure password, how your privacy should be there, how you handle the availability issues, how your physical device should be hardened. So these are the typical 10 guidelines are there for an IoT product. And one needs to infer from those guidelines how does that imply to your actual product over there, right? So from those top 10 things, if you apply those things, it makes sure that you are covering major aspects of the security over there. And again, the underneath of everything is basically the CI triad, what we call as a confidentiality, integrity, and availability. It also has something called as a ISVS, stands for IoT Security Verification Standard, meaning if you want to assess some of the IoT security product from the security perspective, there are certain steps that they have given, and you can follow them to verify some of the products on the security perspective. Then there is a very big organization called as the IoT Security Foundation, and they have the IoT Security Compliance Framework, where it covers each and everything from the business processes for the IoT product, the device hardware, the device software, the firmware, the OS part, the web part, cloud part, the encryption part, the privacy part. Each and everything has been covered as a checklist, right? It is again available for the free as well, and you can follow that. Then there is something called the GSMA. So the GSM technology that we follow, right? The Global System for Mobile Communication, that organization comes with the IoT security guidelines. And I think I'll discuss that in detail in subsequent slide. Then there is something called as the ITSI EN 303645. This is basically a standard IoT security standard for consumer products. So like you have a refrigerator, washing machine, and home automation products. So all these consumer products needs to be secure, and these are basically kind of the standards for that. Now coming to the aim of these particular standards or guidelines, is very important that IoT being a diversified areas, right? So if you go to the automotive part, you again have IoT, healthcare, there is a IoT, and all of these the areas in which if you try to unify the security models, these guidelines will certainly help you in doing that. If you just go detail into some of the guidelines, I just speak about the GSMA, right? So we'll just explore this GSMA in a short, and then you will understand how it is important for the product to have such kind of guidelines. So here, if you observe, so this GSMA provides certain kind of documents. So here mention something called as a CLP. CLP stands for Connected Living Program, and they have these 5 documents, as you can see, as an overview of guidelines, right? Security guidelines for IoT service ecosystem. There is something called as the endpoint ecosystem, right? So when we say a IoT product as a device, it considers to be the actual IoT endpoint ecosystem in this particular perspective. Also, when we say the cloud technology or kind of a web application or some kind of the big gateways that we have for an IoT perspective, they come under the IoT service ecosystem. And they also have given something called as a IoT security assessment checklist, meaning if you follow those things, you will make sure that you are getting most of the required security guidelines for an IoT product. So whether you are a developer or you are doing the verification on those products, you still can achieve those things. And of course, from the network perspective, kind of a cellular network perspective, since GSMA comes from that background, they have the guidelines for network operators as well. So these were the actual documents, right? Again, they are available for free, and one can also go and check on that. Right? So now, as I spoke about the basic CI tribe, right? So these are the security challenges, the availability, integrity, and the privacy part, the confidentiality. It is the different, the names for the CI tribe. So basically, when we try to go for availability, we make sure that there is a constant connectivity between the IoT devices as per the actual architecture, right? Then when you go to the identity, it makes sure that the authenticate device should able to communicate for the end user. When it comes to privacy part, that basically kind of a confidentiality. So it's basically reducing the harm, right? The individual user should maintain their own privacy of the data. So these are the things. Now, this particular GSMA IoT model follows the architecture as you can see in this particular diagram, where the architecture is divided into 3-4 segments. So on the one part, you have these APIs where or the user experience, where user trying to access some of the products through either a web part or a mobile part, those things. And that is basically linked to the IoT service ecosystem that includes all the web services, web APIs, cloud, and the mobile applications. Then you have a communication layer, whether it's a cellular or a short range communication or a long range of the Wi-Fi or those things that will define as per the use case. And the actual IoT device, what we call as an endpoint ecosystem over here. So this is how the basic thing that we're discussing is about the service ecosystem and the endpoint ecosystem in that scenario. So what they do is basically this GSMA try to address kind of the security threats from a recommendation perspective. So if you observe, I have listed some of the attacks from the critical perspective, high perspective, medium, and low. But when you explain, right, ideally, if you feel that when we say a low, it means that these are attacks which doesn't cause the harm to that. Right? But it is not the same meaning over here. So what risk assessment means in this particular scenario is like, if you look at the critical section, it has mentioned that what are the things that comes into the picture. So it makes sure that your IoT devices, when it goes to critical recommendations, should have the secure bootloader. So secure bootloader is something where you have certain stages of bootloader, and eventually the bootloader makes sure that the authenticated firmware gets executed when the system is booting up. Right? So for that, you need to take a the hash part of the particular main application firmware, and then the secure bootloader will actually just verify whether the same hash is there or not, and based on that, it will allow the access to the main application firmware. Then there is something called as a proven TRNG. TRNG stands for True Random Number Generator. So when you are doing some kind of cryptographic operations or any kind of some security operations, this particular true random number generator is much important, and most of your ARM devices and those things will come under such kind of MCUs over there. Then it also looks for some of the critical sections of memory to be locked. So you can go for a memory protection unit, or you can have a OTP or one-time programmable unit into some sections of the memory part. So this way, these are some of the recommendations which are critical. What does that mean in this context is that whoever is trying to follow this particular GSMA guidelines, right, will have to follow all the critical requirements, right? So all the things I mentioned needs to be followed as per the recommendations from this GSMA, right? Now, what does it mean by high-end video? So let us say, now take an example that we have one IoT devices which is going into some of the manufacturing industry, and you're tracking and tracing some of the few things over there. Now, if the operation is very critical, let's say petroleum industry, where you track and trace few of the critical, people as well as the assets over there. So the next recommendation comes is like you first follow all the critical recommendations. On top of that, you follow something called as a high recommendations, meaning you should have the secure over the air update. You should have a tamper resisting case, right? So someone should not go tamper and basically clean your memory or extract something from your endpoint ecosystem over there. Similarly, if on a still higher level, if you go, you have the medium recommendations, meaning you should have the OS level security and all your debugging ports should be actually disabled. And if you go for the mission critical system, like as I've spoken about the nuclear security part, right? So it is something called denial of service, where you are not getting access to the network or any of the device hardware for that matter, and it should be protected from those device protection. As well as there is something called as a cold boot attack, meaning, so let us say if you turn off your PC for a few seconds, there is still heat over there, right, into the RAM part over there. And someone tried to spray with certain chemicals, and you can still retain the memory for some amount of time. And that way you can extract the data from your RAM. So this is what the cold boot attack is. And from those perspective and those mission critical operations, you should follow such recommendations as well. And these are again based on your existing architecture. You create a threat model and a risk assessment for that. And how we can effectively use these things. So again, starting from that, first of all, you should be clear in how your system design is, how your technical model is, what are the actual architecture you're following. Reviewing that in existing technical model, what are the security measures are there? Are there any security measures at the moment? If it is not, you evaluate those recommendations based on this GSMA and implement those recommendations based on the class in which you are trying to apply those things. And of course, the security is not a one-time thing. You have to implement it again and again, because there will be certain new attacks that will come into the picture after a few months, and you have to take a recommendation remediations for that as well. Right? So this cycle keeps on updating over a period of time from a IoT security product perspective. Right? So let's take a case study to understand these security guidelines better. Right? So take an example that we have a BLE beacons, the Bluetooth beacons for the asset tracking. Right? So assume that there are different assets into the manufacturing industry which you track. So asset will be basically fixed with BLE beacons, and these BLE beacons will have certain sensors like accelerometer, temperature, humidity. And eventually, since BLE is an advertisement mode, they keep on sending some advertisement data. And there are IoT gateways who are responsible for scanning all those BLE beacons, and in turn, scanning and pushing that data serially to the Wi-Fi module. And then Wi-Fi gets connected to either your what we call as on-premise server or to the cloud server as well. So based on this connectivity, if you consider this architecture, how we can think from the security perspective. So here what happens is like the first part, as we spoke about the BLE beacons, they will come under the category of the endpoint device, a typical IoT device where we have a MCU sensor and a BLE beacon. And the backend part where we have a IoT gateway where BLE beacons are sending some data from those sensors, and IoT gateway will have its own BLE scanner, which is scan data. It will get all the identification of the data, identification of the particular device, who that device belongs to, and all the data required for that, and push that data either to the web server or a thick and application or a workstation. And again, depends on the use case over there. So the backside over here, this is what we call as a service ecosystem, and this part is called as an endpoint ecosystem for an IoT system. Now, what the security model should think from the attack perspective. So endpoint can think from the perspective, right, if the device is being cloned, right? If the endpoint impersonated, meaning that let us say that there is a kind of the machine which doing some of the critical vibration measurement. It has been addressed as some device ID, and if someone is tampering with that particular ID, or someone is cloning that ID into something other device, right? So that is called as the endpoint impersonation. Also, some of the data that is being stored on the device or sending from the device to the cloud part, right? So that need to be private over there, right? Meant to the privacy over there. So these are the again security threats that can happen to the particular endpoint devices. And on the service perspective, so again there are certain APIs that can be hacked, right? There can be a data exploitation because since there are a lot of data coming from different IoT devices, we need to store that data into the servers over there or databases over there. So that can be actually exploited. And again, if the server is being compromised, right? So that is basically the availability issue. So these are the typical attacks or the threats for that existing architecture. So how we can solve those particular problems? If we follow the guidelines like GSMA, where they can suggest on the encryption of the firmware, we can lock the firmware. Possibly we can have a OTP memory where you flash it once, as well as there is something called as different levels of the security from the ports perspective, the debug perspective, so that the read and write functions for the external users is not there. Also, when you are sending some data from the sensors from device IDs, so for example, let us say it is tracking the people as well in the complete manufacturing plant. Now, eventually it is expected that each and every one who is sending the data should be encrypted, right? And those encryption things should be sent to the server actually. And considering the fact that there are critical assets, if the device is getting compromised, right? So we should have a tamper resistance case. So there are certain attacks on the hardware called as a fault injection attack, where you can actually introduce a fault in your existing system, which can basically clear your RAM as well. So these kind of the considerations we can take from this perspective. And of course, from the service perspective, right? So we should have the architecture which separates all the things. So there should be the proper scalability into those classes of the services, as well as there should be a proper authentication mechanism for the databases for them. So this can be kind of security recommendations one can follow. So this was just the introduction to the compliance and the standards part. Now we'll start jumping into the hardware part, right, which is more interesting stuff. So what we'll do is we'll start discussing about what are the debug ports and what are the buses over there. So Appar has covered all those attack surface, and we'll try to address the debug and debug ports part over there. So eventually, if you go to any of the IoT devices, it is likely if you open over there, most likely you will get this particular UART interface. So if all of you belong to the embedded systems or the electronics part, I'm sure you must have worked on some of the microcontrollers where you must have done the communication between that particular microcontroller with the PC, sending a data over a UART port, what we call as a universal asynchronous receive transmit. And as a result of that, basically, you are communicating, sending a data from a computer to the microcontroller and vice versa. Considering the fact about the hardware devices, right? So there are some of the debug ports, or there are certain bus communication that happens on the hardware device. So generally, UART is always the base of any of the embedded systems or a very basic level protocol, which is ideally to be found in most of IoT devices. Then if you, let us say, you have other peripherals like sensors or the memory part or an SD card in your IoT systems, likely you have these I2C or SPI interface, right? So these are the bus communications which are used for different purpose. And again, from the product development perspective, right? When you have a heavy number of production to be manufactured, like 10,000, 20,000 or 1 lakh quantity from an IoT devices, you need to have a particular process where the production people should be able to debug the things once the production is done. And for that matter, we have the ZTAG and the SWD interfaces on a microcontroller. So of course, it started late from the AVR series, but most of the ARM technology comes with this inbuilt ZTAG and SWD ports, right? So these are the typical hardware debug ports. Though looking from the production perspective of a IoT device, this looks very awesome and helps the IoT manufacturers to make life easy, but it is posing a challenge from the security perspective. And we will focus on the UART, how one can hack the UART and get access to the complete shell of the problem. So we'll just discuss few things about the UART protocol. So I believe we must have gone through those things, but to get into that scenario, let's discuss some of the key aspects of the UART protocol. So when we say a UART communication, it is basically also called as a USART sometimes, what we call as a universal synchronous asynchronous receive transmit, or only UART part, universal asynchronous receive transmit. So this way we have kind of the two-way communication between the transmitter and a receiver, and it is one of the most fundamental protocol. It doesn't expect kind of any kind of acknowledgement from a receiver or transmit. So if you happen to work on I2C interface, there is a lot of pain of getting the acknowledgement when you transmit something from a master to slave or a vice versa, right? If it is not there, again you have to resend a few things over there. So that is the challenge. But here you have the direct hardware interfaces between the two systems or the two devices, and you are basically communicating over there. So this way, if you look for, when you have the UART communication, you have basically the three major pins, right? Which is the transmit, receive, and the ground. The ground is basically the reference point. If you are measuring some voltages, ground is always a reference. And here, if you observe the, let us consider this particular guy as transmit, and the left part is a transmitter, right part is a receiver. So when the left guy is transmitting something, it should be connected to the receive part of the second one, right? So it is basically the cross connection for the communication to happen flawlessly. If you are connecting TX to TX and RX to RX, it is not going to work at all. The reason being, at the background, they have the transmit and the receive buffer individually. So the data that is being sent will be into the transmit buffer, and that is being received into the receive buffer for that matter. So now coming to the format of this particular UART part, right? So ideally the UART is said to be a kind of a character communication where you are standards saying the 8 bits of data. But of course, when it had started with always the 5 bits of data. You can go to 5 to 9 bits as well of the data communication. But when you start communication, since it's a universal asynchronous communication. When you say asynchronous, it means that there is no reference clock for that. And when you don't have such kind of reference clock, what we need is kind of some of the reference bits to make sure the data is being communicated properly. And for that thing, what we do is basically have a start bit, and we send 8 bits of data, or whatever the format you have, 5 bits, 8 bits, whatever format. And then after that 8 bits of data, again you send a stop. So this is a standard format UART follows. Again, for the error correction and those part, we can use the parity bit, having the even or odd parity, right? So this way the frame is basically getting communicated. Now, other thing that comes into the picture is like how, at what rate are you communicating with the other system, and that is what we call as a baud rate. Now, when we say baud, it is the number of symbol of bits, but here what we consider is the number of bits that we are transmitting. So baud and bits is the same at the, and this has been generated basically, since in a microcontroller, though this is an asynchronous communication, generally in most of the ARM technology, those things, right? We have the two buses. One is called as a advanced high-speed bus, and what we call as the advanced peripheral bus. Now, this advanced high-speed bus is basically driven by the complete clock and your PLL system, and eventually it derives the clock from that. Now, this peripherals, when you have a UART communication, though it does not have any clock for a reference, but to run the particular system, right, we need a clock. And this particular baud rate, so there is a 9600 bauds per second, right? It is basically getting, generated as a reference clock. So whatever the clock your peripheral is using, from that you are generating with some formulas given in the data sheet, will generate particular baud rates, right? So these are the one of the things when you are communicating, meaning that let us say the device is trying to transmit at, let's say, 38400. But eventually at the receive part, if you are trying to listen to 9600, it is not going to work, right? You will see the complete garbage. And if you go to 115200, you won't get anything out of it, right? So you need to maintain the equal speed between transmitter and receiver. And for that matter, we have these baud rates. Now, this is all the basics of the UART I have discussed. Now, based on these particular features of the UART, what are the different attacks that has happened on the UART, right? So one way is like trying to get access to the UART shell. So if someone is trying to find the UART pins and trying to, extract actual firmware from it, Isn't that's a very dangerous thing over there? Then other way is like possibly you must have used, if you're from electronics background or instrumentation background, you might have used the logic analyzer for debugging purpose or just finding out okay how your clock signals are being there. And the same device can be used by an attacker to basically connect to the any of IoT device and basically snip the communication, what is happening over there. And that way actually you can tamper the signal over there. So if you observe this particular diagram of the UART snipping, where it is clearly shown that okay, you select a particular channel and what is the baud rate at which you're communicating. And as we discussed about the stop bit and the 8 bits of data or the no parity bit rate. So all these things have been mentioned with this logic analyzer. And as a result, if you observe that, okay, on this particular channel 0 and 1, I can see the receive and transmit. And based on this particular pattern of the data, I can just make out that what is the data that is being communicated, right? So this is just a character that I have shown. But eventually, if you are sending the strings over there, what can do is like basically connect a logic analyzer and get all these clock signals under, not clock signal, get all those signals on this logic analyzer, and you can basically save it in your file and understand what is the communication happening between the two systems. Right? So UART snipping is one attack, a simple attack one can do. So to give an the thought process behind this accessing the UART shell. Right? So consider for the fact that okay, let us see if you have worked even on the Raspberry Pi. So on the Raspberry Pi, if you are just booted up the system and started over there, so there is a sudo rasbi config in which you go and basically initiate kind of the serial communication. And then if you want to communicate to the serial to the device, possibly you find those 4 pins where you have the voltage, where you have the ground pin, where you have a receive and a transmit pin, which is the standard UART pins. And if you observe this particular figure, right, so people, what they have done is like, this is a kind of a router. And if you take close look at here and a right hand over here, we can see these 4 pins coming out. Right? So assume that this ready-made product is there with you and you want to really hack into it. Right? You cut open this particular product, you tear down the product, and as a result, what you see is okay, these 4 pins are there. And as a very intuitive understanding, you see that okay, this can be a UART port. And let me check out how I can access the UART pins of this particular device. And as a result, the same pins, what people have done is like you use simple USB to UART converter, connect your TX RX pins over there, and possibly play with a different baud rates like the standard baud rates what we have 96003840115200, and try to access the shell over there. And as you can see on the right hand, that people have got successfully the actual root shell of that, right? And you can basically log in into the shell as well, right? So this way the UART attack can be done. Right? So now when we come to actually interfacing here, what I mean by interfacing, like trying to perform attacks on this UART, right? What are the 2 main challenges that you will face, right? First is the identification of the pin, because assuming that I have the 4 pins, one is VCC, other is ground, other is a transmit, other receive. How will you identify which pin is what? And the next part is what is the baud rate, right? So guessing is one thing, but what could be the technical things one can think and solve those particular challenges? So the first step is like how we identify the pins. So the possible ways, like first of all, start looking into the combination of 4 pins and club it together. That is the first part, as I discussed in the previous slide. Right? Now there are 2 methods from the manual perspective and single method from an automotive perspective. We'll discuss both of them. So let us say if you want to go with a manual method, right? What you need with the manual method is like you simply need a digital multimeter and you simply need to perform the conductivity test. Right? So how do we do that? So the first step is to conductivity test will happen. We will get a ground and a VCC part. And the second method or rather step for that is analyzing the pin voltage. Meaning the VCC will have a 3.3 volt or a 5 volts. That's going to standard for my IoT product. What we need to identify is like the TX, the voltage at the transmit pin and the voltage at the receive pin. And let us see how we can identify those pins both. So here we can see so some of the things you need to hack the UART codes. So possibly you need the multimeter, some of the wires, right? Of course, you need a kind of a flashlight to identify the pins, because different product comes with different kind of debug headers, which can be challenging for the moment. And you can have kind of a USB to UART converter. Here I have shown something called XClarity Nano, which is our own product, and it can basically convert multiple protocol. I'll discuss that in a moment as well. Right? So this is basically the USB to UART converter, and it is not only UART converter. So it also supports I2C SPI, the SWN and ZOF, meaning if I connect this particular device to my PC and the pinouts to the respective interfaces. So for example, if I want to hack into I2C part, I can simply just from a datasheet, I can find out the I2C pins of, let's say, a memory, and connect my I2C pins of this XClarity Nano over there, and run some utility, what we call as XClarity framework, which is the open source framework. You can go and download that as well. And with that, we have certain written some plugins. You can access those things, and eventually, as a result, you can access those peripherals over there. So as a here, what we are looking for is like using this XClarity Nano, you can able to access the UART code as well. So another tool which is basically used for automated method. Just before going into the manual method, let me discuss the tools, and then we'll go to actual methods how this work. So another challenge, as I've spoken about, finding the pins, right? Which pin is doing what? So we again have a product called as XClarity Bus Auditor, where you can basically connect the, as you can see in the figure, you can see that like there are a number of pins that is coming out, and you can connect these pins to debug headers and power it up, and eventually this particular device will tell you which pin is a receive, which pin is transmit, which pin is ground, which pin is basically the VCC part, right? Similarly, not only for UART, you can also do it for ZTAG. So if you want to hack the ZTAG or extract the firmware from a ZTAG, this can help you to identify which pin is of the ZTAGs, or which pin is for the matter I2C itself. Right? So this is one of the tool for automated method to identification for the pins. Now let us understand the actual hacking process of manual method, right? Where first of all we need to identify which pin is doing what. So first of all, what we'll do, so as an electronics engineer, right, what we do is like we try to identify which are the power sources. So first we'll try to identify the ground planes, which is the easiest thing. So you can do basically kind of a continuity test. Right? So you can see there as a continuity, as a sound symbol in the bottom image, right? So this particularly conveys that, okay, I can see the continuity between different grounds. Similarly, I can identify the voltage BCC pin as well, right? So out of 4 pins now, you have removed 2 pins. What now remaining is like RX and a TX part. So here, how to identify RX, TX? So again, so as we have spoken about the ground part identity, so this is a simple way. It's a continuity test that we do. So let me run into it. Now let's just focus on the transmit part. Okay. So what happens is, assuming that we have a certain voltage like 3.3 volts or a 5 volts for that matter. Okay. So multimeter range, if you observe, at the 20 volts will keep our arrow and trying to measure the one of the pins from the rest of the 2 pins, right? So how to identify which is a transmit pin? So eventually, let us assume that the device is sending a 3.3 volt signal. When it goes to the transmit pin, you will observe the voltage around, let's say, 2.96, 2.8 or 3 or so. And that way you can say, okay, this seems to be the transmit pin for that matter. On the other hand, to identify is a receive pin is quite difficult, because receive pin does not show any kind of voltage immediately. Possibly we get 0.01, 0.1 or 0.2 volts over there. And that is basically kind of an indication that where you have a least amount of voltage is the receive pin. So this way, manually you can identify these particular pins over there. Okay. So as you can see, if you want to know interface, once you identify these interfaces from this particular product, right, we'll be showing the video now in a few moments how this hacking happened. But just to explain you better, so what is the next job? Once let us assume that this is particular kind of a camera that will be showing you, and this has this particular debug ports available on the product. Right? So intuitively, so this is basically done by us. The hacking does by us only. And over here, if you observe, the 4 pins are there, and we see that okay, this is intuitively kind of the UART code, and we did the same methods what I discussed, like identifying ground pin, the VCC pin, right, removing those from the combinations, and then use finding out the TX and RX pins. Now, once you have this TX and RX pins, you can use the USB to UART converter, where you connect TX, RX in a cross fashion and have a common ground across that. Once you have this setup ready, you can use certain utilities. Right? These utilities like Minicom or Picocom or a screen, where you try to run particular kind of a this particular access device on certain baud rates. Right? So assume, let's say most of this device by default comes either with 115200 watts or 9600 watts. So this is something default one attacker can do over there. Now coming to basically like there is a challenge. For example, let us say if you are not able to get to the exact baud rate. Right? So what is the solution for that? So there is a one famous guy called as a Craig Hefner. He has written an excellent script for baud rate identification. This is the the source for that. You can actually go and check over there. With this particular script running, it will tell you what is the baud rate the device is actually communicating. And once you find the particular baud rate, simply use the baud rate in your command and access the device. So this way you can do those things, right? So these are the typical commands that one can do. So this was the manual method. Now with the automatic method, what we can do is like the ground truth is something that we can actually access very easily with the zero board, and the bus auditor that had shown in the previous part, right? So that is basically does the job of finding those particular pins, right? Rest of the pins. So it scans for rest of the pins. It tells which is the transmit pin, which is the receive pin, and then once you have the access to the pin, so just to simplify it again, that the first step of hacking is like scanning for the pins. When you scan, you identify the pin numbers, you identify the baud rate. Once you're done with these two things, you connect your USB to UART converter, and then go for connecting the TX-RX in a crosspair, connect it to your system and access the root or access the cell. So this is what we're going to hack into it. Now I'll play a video. So let's understand. I'll give a voiceover that what is actually happening. So to begin with that, as you can see, there are two screens. One is something where we are doing the hardware stuff, and on the other part, we have this particular framework called as the expertise framework. So let me play the video. Yeah. So this is basically a network-enabled camera, and for which we had identified kind of the pins of the UART. As you can see, there are 4 pins. These 4 pins, right? Intuitively, it's a UART pin. Right? Of course, we found the same thing. Now, our job is to identify each and every pin. The first thing what we can do is to identify which is a ground pin. And ideally, if you see any body metallic part of product in an IoT product, so that metal part is a ground reference. So with this particular continuity test with the body metal part just now happened, right? The ground has been identified. Now we'll use this particular exploitative bus auditor, which has again a ground pin. We'll first connect that ground pin. Let's first power up this device. Connect the ground pin. Now the next part is like we have the rest of the 3 pins. We are basically interested in receive and transmit pin. So let's connect any two random pins from this particular bus auditor to the rest of the pins. And now what we'll do is power up the camera. And try accessing this particular bus auditor that has been connected. So this is our XPIT framework, and there is certain kind of plugins that is written. It's called the UDYAM' scan. What it does is works on let's the voltage that you're working on. So let's like 3.3 volts. So here, if you observe, it is trying to understand the start pin and end pin. So you can see we have a start pin 0 and pin 1, meaning the pin number 0. So the TX pin 0, RX pin 1. What does that mean is that the bus auditor pin number 0 connected to TX, bus auditor pin number 1 connected to receive. As well, it has identified the baud rate 38400. Now this way we have solved the problem of identification of the baud rate as well as the pin configurations. So this is the first step. Now the next task is basically to connect the USB to UART converter. In this scenario, we have used our own product called as XPIT Nano. Right? This is the XPIT Nano converter, and for the pins that we have identified as TX and RX, will be connecting to the respective pins from the XPIT Nano. That is, the RX of the XPIT Nano will be connected to the TX of the camera, and the RX of the camera will be connected to the transmit of the XPIT Nano, and the ground will be common for that matter. Let us power up the device, and since it's a UART thing, you can use the utility like Pinicom screen. Right? So using the screen, and we already know this kind of like this is a Linux system, so you can identify which port is this like USB 0, and we have already identified the baud rate. So the baud rate will be 38400. We try to access that, and you will observe soon we'll be getting some logs. So you can see this particular booting process of the device. Keep on observing what things are getting logged into it. So these are all initial boot logs. Even the initial boot logs will convey a lot of information of the firmware architecture. So some discovery command it is sending, and as a output, you can see when you do the ls on this particular thing, it has basically a Linux file system. So we have access to the Linux file system. So what we'll try to do is we try to find some of the credentials with the commands. Right? So what is happening is we're typing something, sending the commands. So since it's a UART, it's a two-way communication happening. Whenever we are sending something, we are also receiving. So that garbage you can see while typing something. Now, if you go into this particular file system, we want to find out where I can have a credentials. So in general, in a Linux file system, we have a etc folder where you are likely to find the credentials. So we have particular kind of the system where, as you can observe, the cat password, there is a file which shows the username is admin and there's a password for that. Okay. So this way, you can actually go and hack the IoT device on a hardware perspective. You can basically reboot a device then. In general, like Now, what we have found is basically the challenging the issue of the confidentiality, meaning you have observed what is the password. Now, since we have a root access of that, one can actually go and change the password. That is the attack to the integrity part. And in turn, assume that someone has doing this attack on some of the home system and changing the password. And let's say this device again packed up and kept as it is. And the user, let's say, comes and it try to access few things. What will happen? There is an availability issue because he does not know what is the actual password has been changed, and that way it is caused the availability issue. That way, the CIA tried of the cybersecurity has been addressed into this IoT part. So this is from my side. Now again, I'll hand over to Apar for the firmware part, and once we're done with the firmware, we can take some Q&As and discuss on that. Thank you very much.
Thank you so much, Yashodhan sir. So now we'll move on to the firmware, what firmware is and how you can, find security issues and how the attackers find security issues and firmware in order to, exploit the device. So we'll look into what is firmware, what are the types of firmware, what a bootloader is, the different type of firmware updates, secure boot and common challenges in firmware analysis. So again, according to the book definition, a type of software that provides control, monitoring, and data manipulation on engineered products and systems. And it is held in non-volatile memory such as ROM, EEPROM, or flash. So in simpler terms, a firmware can be defined as the soul of an embedded product. It is basically the code or a full-fledged OS that is running onto the device and is what basically determines how the device is going to behave, what are the logics or what are the features that are implemented onto a particular device microcontroller. So firmware can be held responsible for all the action the device takes or all the services, all the different features that the device basically provides. Again, it is stored in the non-volatile memory on the device PCB itself. It can be ROM, EEPROM, or different kind of flash memory depending on how the device is designed. And there are many different types of firmwares, but broadly classifying for today's session, we'll talk about three of the major types of firmware. You have the bare metal firmware, you have the OS-based firmware, and then finally you have the RTOS firmware. So looking into each of it one by one. So first we have the bare metal firmware. So a bare metal firmware again would by design would run on microcontrollers, and on the right hand side, as you can see, from the diagram, you have the hardware and then you have the application. So the bare metal firmware directly resides and run on the device hardware itself, and that is the reason why it has a flat memory model, which basically means the entire firmware is onto the device memory itself. You have different memory blocks. For example, let's say for some a memory block is specifically there for the your peripherals, critical peripherals that are being called upon at the time of boot. Or then you have the flash memory. Then you have the user land or the user facing programs and other binaries. It is more suitable as it is more of a lightweight implementation of firmware, and bare metal is very specific, not very specific, but still a lightweight implementation and specific to low computational targeted towards low computational applications. You have tool chains that are provided by the vendors. Some of the examples of bare metal firmware include EmbedOS, Casper, LiveOpen, CM3, and Zephyr. You'll find these bare metal firmwares on a lot of smartwatches that are out there in the market, your microwave ovens, and your washing machines. So this is a very high level overview for what a bare metal firmware is. Now moving on to what a full-fledged operating system based firmware is. So operating system firmware looks like overlooks all device functionality. It is like your complete operating system, for example, any Unix based or your Windows or Mac OS that you run on your uh, notebooks and desktops. It is something similar to that. Again, the hardware is microprocessor where it is implemented, as you have observed the previous one, which means the bare metal one usually runs on your micro controllers. This is more specific towards microprocessor. Since I mentioned that a lot of computation goes into while you're talking about a full-fledged OS. You have virtual memory protection uh, on your full-fledged OS-based firmware. That means not all parts of the memories are accessible, for the user. These are very specific to the system, and only the system can access some of the memory partition. Again, heavy processing, more advanced OS features required because it is like a full-fledged OS, and you have your probably devices using these have GUIs, web servers running on them. So again, it requires heavy processing and and a lot of you know devices that have a lot of feature usually opt for OS-based firmware. Some of the examples of OS-based firmwares include your Linux, your embedded Linux. Not very different from the Linux we use on a day-to-day basis, but more of a strict version of the same Linux. Um, then you have Windows IoT. You have also Windows CE as some of the examples of device-based operating systems. These are usually used in routers, your smart cameras, your smart televisions, and a lot of places. So of the devices that have high computation, you'll find 80% of them using a full-fledged OS on them. Now moving on to the next one is the RTOS, which basically stands for real-time operating system firmware. These are designed to provide a deterministic execution pattern, which means a high priority task will be executed first, and the remaining task would go on the on hold while this high priority task is being executed. It basically runs on the agenda of multi-threading. So again, multi-threading, you have your processors, you have your processes, and different threads are being executed at the same time for that process in order to keep the real-time element of the firmware, real-time element of the program. It fits into both category. It can be a full-fledged OS as well as bare metal. And since there is a lot of real-time data, that is being processed by these firmware, and the actions on that real-time data has to be taken by the this type of firmware. So uh, that is why the multi-thread. Um, uh, some of the classic examples of RTOS firmware includes your real, FreeRTOS, ThreadX, VxWorks, QNX, just to mention a few. It is used in your air traffic control system, command control system, automotive system. So the infotainment system in your car is actually a RTOS based firmware, depending on how high end your car is, because in some of the cars you can um, also control the car functionalities from the infotainment system. So again, that makes those infotainment system based on the RTOS firmware. Now talking about the bootloader. So, while we're talking about a full-fledged OS or a full-fledged firmware, it would not just be, the OS or the root file system of that particular like firmware, or just the, the bare metal code of that particular firmware, but it would come in package. So it would have your bootloader, it would have your operating system, it would have your user space elements all in one. That is what is a full-fledged base firmware. So the first stage is called the bootloader. It's kind of a piece of software that is responsible for starting off a computer or a device. It checks for uh, whether the hardware is working properly fine, if it is properly initialized or not. And it is responsible for loading the main OS kernel as well. Some of the examples are Red Boot and Qboot. And first stage firmware would basically ensure first stage firmware would basically read from your memory, and it would check if all the hardware is properly initialized or not. Then it would once that is done, it would then call up the second stage bootloader. Then second stage bootloader would basically in turn call up the kernel. The kernel will basically uh, define the kernel parameters, and also call the init processes for initialization of the system. And then once init is done, you get your um, your proper OS onto the device, which basically is all the GUI and all the uh, other functionalities that are part of the device. Some of the other examples of bootloader that you probably might have come across is Boot Manager, NTDLR, NTLDLR, which is your NT loader, your Barebox bootloader, your boot.efi, your bootx, which was one of the popular bootloaders uh, in the Mac era when Macs were making. Then finally, your evergreen grand unified bootloader, which is your Grub, which you'll come across, in your Unix-based operating systems such as Linux. So, these are some of the bootloader examples. And as I mentioned, the OS basically consists of not just the firmware. Full-fledged OS would not just basically consist of the file system, but also the user space binary and bootloader. So this is what it would basically look like. So for the bootloader, I already gave you examples. Likewise, for the operating system, you can have Linux, Windows CE, Cisco OS. Then your user space consists of various files and directories, and various compression techniques or arrangement of file system varies from device to device. And some of the examples for compression is Lisma, gzip, bzip, and zip itself. And for the file system, for the commonly used ones that we come across in the IT device, you have your SCOSH-FS, CRAM-FS, JFFS2, YAFFS2, and so on. The list goes on. So these were some of the examples on how the full-fledged OS basically looks like. Then something called the firmware updates. The firmware updates are referred to as FOTA or SUOTA. FOTA, which stands for firmware update over the air, which is one of the common used way of calling when a device is basically having a firmware update. Even in our mobile devices, we have notifications for FOTA. These devices can update, the IT devices can update firmware from, via various ways. But the most common and widely used way is via the cloud. So, any server that is directly interacting with the device would basically send a firmware onto the device, and and basically the device will take up that firmware, check whether it is signed by the same private key uh, of which the public key it is burned with, assuming that it is a secure way of updating the firmware. So you have asymmetric encryption techniques being used while a secure firmware update is taking place. So the device manufacturer would basically have the private key, and the device, while it is burned with the firmware, would also be burned with the public key for the same pair. And while sending these updates, uh, the device manufacturer would basically sign the firmware with the private key, and onto the device the public key basically unencrypts it and um, loads it onto the device. So this is how your firmware update works while the cloud or the server is directly interacting with the device. Let's say if the device does not have that kind of functionality, if it does not have your eSIM feature or LTE enabled device. So basically, it would communicate with a middle device. It can be either a mobile or a hub or a gateway. A hub or a gateway is usually observed while we talk about in terms of the home automation scenarios where all these devices are connected to one hub or one gateway. So in that case, the server would first send the update to the mobile device or the gateway, and from the gateway, the update is distributed over to the device. Um, and last but not the least, you have USB firmware update. So uh, you can update the firmware via USB as well. You can download the firmware zip or firmware binary from the support of the website and basically connect your device, and you can update the firmware via that way, or you can also update your firmware via the web interface like you see in the routers. So the routers have embedded web servers running on them. You go to the home IP. In the home IP, you basically log in, and you have a section where you can do the software update or the firmware update onto the device. And basically, when you click it, uh, uh, the the router basically gets the firmware update directly from the device manufacturer. Some of the challenges that we face when we talk about firmwares is it is very diverse in terms of hardware. You have different CPU architectures, you have different memory management units, you have different ways of execution on RAM, storage strategies, debugging capabilities, software update mechanisms. So while working with firmwares, we see that there is a lot of variety that we come across, and a lot of different chip manufacturers might have their own custom architectures that they work with. So reverse engineering when analyzing firmware becomes a challenge in that case. Software provided by many vendors, again, you'll have different operating system, different tool chains, you have different device drivers and SDK. Everyone implementing their own thing in different way. Is what causes a challenge when we talk about firmware security. Talking about tools of trade, some of the tools that you can use or the attackers use for analyzing firmwares. The first and the major one is called binwalk. It is also a Unix utility. You can find it pre-installed on your Linux system. It is basically a simple firmware extraction tool where it has even simpler interface. Simply just by typing in binwalk -e, and naming the firmware or giving the location of that firmware binary file, you can extract the firmware from the binary block. You can read more about binwalk on www.binwalk.org. Binwalk, the company that created binwalk called Reform Labs was recently bought by Microsoft. So since Microsoft was venturing into IoT, so this is one of their tools, and it would look something like this. You will type in binwalk, and here we have given the binary that is ktips.bin, and in turn it would give you what kind of description on the different addresses, that what file system is being used, um, what compression is being used, and stuff like that. So also, you can use different handles that come along with binwalk. For example, binwalk -caps e, and it would basically give you a graph of the entropy of the firmware. Next tool that we talk about is the firmware Mandke. Again, it is a very simple tool to use, and it is a combination of firmware tools. You can find more about it on the Google code repository. So it is basically used to extract and modify firmwares, and a proper way, a proper tool to check if the root of trust is implemented on a device or not. So you can take a real firmware, original firmware from the device, modify it, and then try to reflash it onto the device, and we check if there is root of trust on the device or not. So here, as you can see, the firmware modkit was run on, again, the key tips a binary extract firmware.sh, and in turn it basically extracts the firmware and stores it onto that particular directory itself. Um, Again, the command for repack is build firmware.sh, and you can do it in the uh, root directory of that extracted firmware. It would again repack it into a binary, and then the attacker or someone who is working with the firmwares can again use that reflash binary. Common problems while we assess firmware is that you don't have the source code. You have to basically you have the binary. You have to again put it into the reverse engineering tools. You have to decompile and disassemble and try to map the functions together in order to understand how the firmware or a particular firmware binary is working. Often we come across working with exotic architectures. As I mentioned, you might come across some microprocessor that has a really weird architecture, and even though they're basically built on top of ARM or x86, but surprisingly they'll have some different elements which would add into the ambiguity while working with these firmwares. The next common problem that we face is set up the device to do dynamic debugging. This is something that I'll discuss with while we talk about the different types of uh, analysis of firmware. And can't we just run a very small portion of the program? Again, something that we'll see in as we go on. I think we have only 5 minutes left, so I'll try to complete this all up. So the tools of trade while reverse engineering a firmware or a particular custom binary or any of the binary that we come across is either we do a static analysis or we do a dynamic analysis. So, so what a static analysis is? In static analysis, we basically take the binary dump, we load it into one of the reverse engineering tools, and without its execution, we try to expose the vulnerability of whatever portion of the source code that we have from the mapping the functions uh, of the particular disassembled and decompiled code that we have. It may not be able to find some of the subtle and complex vulnerabilities because we are not doing this in an execution environment. It is just a static piece of code that we have found, and it could also have many false positive as well. Again, talking about the second approach of analyzing a firmware is dynamic analysis. Here, what we do is the security analysts or hackers basically examine and manipulate the firmware while the device is in execution state. Now, this can be either by emulating a particular firmware or a particular binary, or this can be done by dynamically debugging a particular device while the uh, firmware is being executed on it. So it can be either way, but more commonly used way is emulating a firmware because hooking debuggers is sometimes not possible on real devices. So what we tend to do is we emulate a particular binary of a particular architecture and then hook the debuggers in order to find something in the execution state. So it is capable of exposing complex vulnerabilities that can be found during only the execution, and it can only find vulnerabilities in part of the device that can be executed. And more extensive and more comprehensive techniques like fuzzing and glitching are some of the glitching, even fault injection. These are some of the things that can only be done while we are assessing the firmware while in dynamic analysis, because we actually need the execution of the firmware in order to find how it reacts to those glitches or to the faults or to the input fuzz data. Um, so tools of trade for static analysis is basically your Ghidra, your Radare2 Pond tools. So if you're a CTF player, you'll definitely know all of these tools. For dynamic analysis, you have UDYAM', which is a code emulator engine, your GDB, multi-arc, which is a GDB debugger for different architectures. Your PON DBG, which is just a wrapper around your GDB, which makes debugging, uh, which assists you in debugging basically. Then you have your Reduxa, which is basically a mutator that you use for generating fuzz data or seed value. Some of the goodies or some of the low-hanging fruits that you can look for in the firmware include the file system, how it is structured. If you have good understanding of the Linux, you will directly, which which directories to directly probe into. Then your custom user space binaries, because these are the binaries that are created by the device manufacturers and have vulnerabilities most likely with them. Your web code, which is whatever web server is using on the client side, you get the source code of all, you get the HTML files of all those displayed webs, the websites from there. Your passwords, your config files, certificate keys, all of these things you'll probably find in the firmware if it is a poorly uh, implemented firmware from a security posture. Some of the challenges that we face while reverse engineering firmwares is again proprietary formats and encryption, firmware encryption if the device firmware is already encrypted. So for proprietary formats, I've come across once I came across a firmware which had directories named A, A, B, B, C, C, D, D, and when I went into those, it had three A's, A, B, 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 B. So, again, proprietary format, some of the vendors implement in order to, create a more secure firmware rather than keeping the actual directory names, which are commonly used. And firmware encryption, again, is a challenge because you have to then understand the decryption routine and then basically again wait for the next port update, or maybe go to the support, and if they have the archive or the legacy firmwares from where the firmware encryption started, you can take that particular firmware and then try to understand what public key is it using and stuff like that. Again, static analysis, talking about it, it is consisting of extraction, strings, heads dump, identifying the instruction set. So you extract the firmware file from the blob that you find, then try to look for interesting strings in the code. You can find passwords and key that way. You just have to look up for some interesting or commonly used strings. You have the heads dump, basically to analyze the file headers, and because not all the files would be identified in just a gist, you have to basically check what headers they have using hexdump, identifying the instruction set, try to identify what type of architecture does the device run on if the chips do not have the exact component ID or component name. So again, some of the tools, as I mentioned, that can help you with firmware analysis is Binwalk, Firmware Modkit, Fact, which is firmware analysis and comparison tool, and John the Ripper. All of these tools are open source, so you can definitely check them out and try it out yourselves. Fact is a really interesting tool because it consists of compilation of various open source firmware analysis tool or binary analysis tools, and combined in such a way that you have to just work on the GUI that is hosted uh, on the local network, and you just have to feed the firmware, and everything is done on the back end. So you can try out Fact as well, even though it is as expected very heavy, but still, if you want to get things done in an easier way, Fact is the name. Binwalk in action. So as you can see here, Binwalk again, you just type in Binwalk, give the name of the firmware binary, and in turn it would give you, what all the components are there available in the firmware. So talking about extracted information analysis, you can extract different data from the firmware that you need to check, as I mentioned, hard-coded credentials, password configuration files, custom scripts and vulnerable internal programs. And you can also modify the firmware according to what needs. Probably add a backdoor to the firmware, and then you can reflash the firmware onto the device. So you can try it out. You know, just try to reflash a device onto your friend's, reflash a firmware onto your friend's device, add a backdoor, and it's a cool and interesting project to work and spy on your friends. Uh, a dynamic analysis, again talking about dynamic analysis, you have binary emulation using Chemo and CH2. You can do fuzzing, you can find issues and all this while you debug um, for where exactly the vulnerability lies. So that was mostly it from the firmware side. I'll talk about an interesting case study, and then I have a few demos for you. So this is a CV 2017-10721, which was that the firmware had a telnet enabled. So this was the product was Shikhar endoscope. Endoscope is basically used to probe into either your industrial system, your car garages, or even human body. Sometimes you send out the endoscope through your esophagus down to your abdomen and stuff in order to check for different medical issues. So it was found that the endoscope firmware had default SSID with default credentials, and this enabled the any user on the same network to brute force a telnet and get access to the device. This is what the endoscope looks like. It was connected to the mobile application in order to view wherever the endoscope was put. And here is a small demo. This was done as part of our internal research, where we found, uh, uh, device having vulnerable firmware and how the attacker was able to uh, exploit these devices. So this is a patient monitor, which basically gives out the vital stats of the patient. So here, as you can see, there was a default, telnet being enabled by default onto this device, and the attacker basically drops a zip file and a script to unzip and execute on the device. So this basically why the attacker was able to, once the device was set it was rebooted and set back into the usual state. It had ransomware installed on it, and this would basically make the device unusable until and unless the ransomware is taken care of. Here in the next demonstration, again, there was this is the same device, and it had a telnet enabled by default in its firmware. Now, um, here the attacker, you can see, was able to log in using default credentials, which was root. Then the firmware, then the attacker on the top drops a ransom binary onto this device, and basically again open the zip file and executes the shell script in order to install the ransomware. And finally, for the last demo for today, we had a AP again a vulnerable firmware. So the attacker was able to fuzz a particular characteristic of the BLE GAT server, and there was proper check on the input data of the firmware. The attacker is basically able to DOS the BP monitoring machine, and in turn does not actually measure the BP of any patient, but rather the air keeps on filling in the um, the pressure armband that is supposedly to be on the arm of the patient. So you could imagine, not in our case, but if it was some elder trying to measure his BP and via BLE, on the device having such an insecure firmware, this could lead to some serious injuries to patient that is using this. So basically, this here the attacker is fuzzing a particular BLE handle, and this leads to no checks on the phone, leads to air getting filled till the user itself or the attacker itself stops the attack. Otherwise, it would was just it kept filling. Yeah, so that was mostly it from our side, and that was it for the hardware and firmware. So if you have any questions, feel free to ask the questions. And I think our time is already up. We have taken 6 minutes extra, so we can now take the questions.